This is the screencast for Monday, September 30th. And so we're going to continue the discussion of amines and derivatives. And now we're going to look at the acidity of the NH bond of an amine. And in the context of deprotonating an amine and then using that as a base for other organic reactions. So the NH bond of a typical amine has a pK of 40. So amines are in general weak acids. And so because they're weak, we have to use a very strong base, such as sodium hydride. Again, that's NH or Na plus and then H minus. So that is called hydride. Or the other strong base is N-butyl lithium, where this carbon is a carbon anion, a carbanion. So we have lithium plus, and then the carbon is minus, and then the rest of the chain. So that's N-butyl lithium. The N stands for normal, which means the negative charge is on carbon number 1 of the chain. So the product of the acid-base reaction shown, whether we're using sodium or lithium, is a metal, diisopropyl amide. In the reaction shown, the metal is going to be lithium. Notice this name, diisopropyl amide. So amide, you're typically used to seeing this carbonyl-based functional group. However, in this context, amide means the nitrogen atom is negatively charged. So when we take the strong base N-butyl lithium plus diisopropylamine, what happens is the carbon anion will deprotonate the NH bond, and we form this base, which is called lithium diisopropyl amide, and it's typically abbreviated LDA. So this is a base that is used to deprotonate other CH functionality. So it's a strong base. It's also a bulky base because of these diisopropyl groups. And what that means is it's non-nucleophilic. So this acts pretty much as a base, not a nucleophile. So it does not add to carbonyl groups. So LDA is a pretty common base. It's generated in the solvent THF, which is a cyclic ether at minus 78 degrees C. So it's used as a base to deprotonate other CH functional groups. We'll spend more time with LDA in Module 3 when we learn about oxidation state 3 functional groups, as well as Module 4 when we learn about deprotonating the alpha carbon next to carbonyl groups. So one other property of amines and derivatives is that they can be separated using liquid-liquid separation. So this is what you've done in lab. So 255, 256 lab, when you use a separatory funnel. And so you have these two phases. So the bottom phase is typically more dense. It's usually water. And the top phase is less dense, and that's typically an organic solvent. So when presented with a mixture of an amine and a neutral compound, it's feasible to separate the two using acid-base chemistry and then solubility principles. The reason this works is that the ammonium salt is now ionic and will be soluble in water. So if we think of say a primary amine, so CH3, NH2 plus HCl, that's going to give us salt. And so salt, that has an ionic bond, which means it's now soluble in water. So if you have a mixture of an amine plus some other neutral compound that's not an amine, you can protonate the amine to form a salt. The salt will go in the water phase, and the neutral compound will stay in the organic phase. So for example, if we're using diethyl ether as the organic solvent, we adjust the pH to the acidic range with aqueous HCl. The amine is protonated to the salt. It goes into the water phase. The organic compound stays in the ether phase. And now what you've done is you've separated that mixture using liquid-liquid extraction. And so once you separate the phases, the aqueous phase is then treated with sodium hydroxide, so the pH is greater than 11. And the reason that is done is you have your ammonium salt, and you want to make it now neutral. And so the pK of this is approximately 10, so that's why we adjust it to 11. And you end up with your neutral amine plus sodium chloride plus water. And then you can back extract that out with diethyl ether to isolate the amine, which is now called the free base. The process is informally known as cracking the salt, and that works because it partitions the amine into the ether phase, and the aqueous phase now contains sodium chloride. So this is important for a process called resolution. It's classical resolution because it basically, you're taking a racemic mixture of one-to-one mixture of stereoisomers called enantiomers, and you can resolve them, that means separate, through an acid-base reaction. One of the most common bases that's used is this alkaloid called brucine. And brucine has two nitrogens. This one's in an amide. This one is a tertiary amine. And we learned about amine basicity. So the tertiary amine of brucine gets protonated when you're treating it with a mixture of enantiomers. And so because this has a bunch of chiral centers, which I'm circling here, when you take your one-to-one mixture of enantiomers and they get protonated, that forms diastereomers. So enantiomers plus brucine now gives you diastereomers. And we know from Organic 1 that diastereomers have different physical and chemical properties. And that's going to allow us to separate the enantiomers. And so that's called resolution. So brucine was discovered in 1819 by Pelletier and Caventou from tree bark of this species here. So here you see some pictures of Pelletier and Caventou, and then the bark of that tree. And in that bark is brucine. So it's harvested and isolated, and it's used as a resolving agent. So if you were given a one-to-one mixture of carboxylic acids, and I'm going to put a star there, where the star means that within that R group, there's a stereo center. And so let's just say the first one's the R enantiomer, and the second one is the S enantiomer. And then you treat with brucine. What you get are these two salts. So R, O minus, and then we'll say HN plus. This is the brucine. And then you get the other salt. Now the brucine's still the same molecule, but that's S. And that mixture now is diastereomeric. And that's going to allow you to separate them, because typically what will happen is one of those diastereomers will be crystalline, and the other enantiomer typically remains in solution from the reaction. So one will precipitate out, and that will allow you to then filter it. And so you've separated the enantiomers through this process called resolution. So now we're going to switch gears here and look at nitrogen not as a base, but as a nucleophile. So how do we get nitrogen into a molecule to make an amine? So one of the first reactions we learned with SN2 chemistry is that ammonia by itself is not a good nucleophile, because essentially it will polyalkylate. So basically what we have to do is protect the nitrogen. So it only has the lone pair available. We don't want all these other hydrogens on it, because that's going to lead to other reactions. So our objective of running any chemical reaction is to get 100% conversion of the starting material to 100% chemical yield of the product. So when we introduce nitrogen into the molecule, there's 3 ways we can do it. And these are typically salts of the form M plus, and then N minus, and then you have these two other groups bonded to the nitrogen that protect it. So the 3 reagents are called sodium azide. That's a nice solid. Potassium thalamide is a solid. And then potassium cyanide, which is a solid. So solid reagents are nice because they're easy to weigh. So you're not dealing with liquids where you have to do a density calculation and then measure by volume. So sodium azide, potassium thalamide, potassium cyanide are all ways of getting nitrogen into the molecule. And so what you see in all of them, you have N minus, N minus. And then in potassium cyanide, the carbon's actually minus, but it's bringing along that nitrogen. So this is actually installing a carbon between the nitrogen. So the 3 reactions that we've learned from Organic 1 are all SN2 reactions, where basically, remember, we have to account for the steric bulk of the electrophile that the nucleophilic nitrogen is reacting with. So in the first one, when we treat with sodium azide, we end up with an azide. The second reaction, potassium thalamide, we end up with a thalamide. And then with potassium cyanide, we end up with a nitrile. And basically what this is forcing us to do is now we have to deprotect the nitrogen. So there's another step that we have to do after if we want to reveal it to the amine. For azides and nitriles, the nitrogen atom must be reduced in oxidation state. And this is typically carried out with a hydride reduction or hydrogenation conditions. So as our starting material, we have bromocyclohexane, which is a secondary bromide. If we treat with sodium azide and DMSO as the solvent, so we have a polar aprotic solvent. Remember, that's what we need for SN2. And then we heat it. We do a substitution of the bromine for the azide. Now, if we want to get to the amine, we have to do a second step, which is a reduction. And we can use lithium aluminum hydride for that in THF. And now we're ending up with cyclohexanamine, which is a primary amine. Notice now in alternative conditions where we're using potassium cyanide, the presence of that carbon atom is now going to homologate or add a carbon to the chain. So here we end up with a nitrile. That carbon is at oxidation state 3. The nitrogen is at a higher oxidation state that needs to be reduced, and we can use hydrogen gas with this nickel catalyst and methanol. And we're still ending up with a primary amine, but notice this carbon that's come along for the ride there. And that carbon's been reduced to oxidation state 1. So between the two, with sodium cyanide, the nitrogen is bonded to the carbon that was bearing the leaving group. Whereas in potassium cyanide, it's now 2 carbons over. So we call that a homologation, the difference between these two species. So in a LEAP question, it says, which of the following electrophiles will react the fastest with sodium azide and acetone? So first thing we want to do is draw out the structures. So 2-chlorobutane, 2-iodo, 2-methylbutane, 1-bromobutane, and then 1-bromo, 2,2-dimethylbutane. The next thing we want to do is classify the nature of the halide. We have a secondary, tertiary, primary. And this is primary as well, but it's also called neopentyl because the carbon next to it has 1, 2, 3 groups. So that's called neopentyl, and it's pretty sterically hindered. So remember, for SN2, the rate trend was methyl greater than primary, greater than secondary, and tertiary is essentially unreactive. So comparing these, we see that the 1-bromobutane is primary, so that's going to react the fastest. And then actually choice B, which is tertiary, and D, which is neopentyl, will not react at all under these conditions. So now that we've formed 1-azidobutane by taking bromobutane with sodium azide and acetone, again, polar aprotic solvent, for SN2, we get the azidobutane. And the question is asking you how many unique sets of hydrogen and their ratio. So we have 1, 2, 3, 4 unique sets. So we can eliminate C, we can eliminate D, and then the ratio of those 4 sets is 2 to 2 to 2 to 3. So we eliminate B, and our answer is A. Again, those sets are all different based on their relationship to the azide group. Even though these three are CH2s, they're in different relations to that nitrogen, so that makes them unique. The next set of conditions is called the Gabriel amine synthesis, which uses potassium thalamide as the nucleophile. So if we take 2-bromopentane, which is a secondary bromide, we use the reagent potassium thalamide in DMF as the solvent. So DMF has this structure. Again, polar aprotic solvent for SN2. We now end up with this species that's called a thalamide. And you can think of a thalamide, once you identify the nitrogen, it has an amide and then another amide, and that group is called an imide. And the rest of the molecule is benzene, so that makes it a phthalimide. And what we need to do is now reduce off the imide part, and the reagent we use for that is called hydrazine. The solvent is ethanol with some heat. And so now that's going to make the primary amine. Again, alternatively, you could make this from the same starting material, but then in 2 steps using sodium azide, and then step 2, lithium aluminum hydride to do the reduction. You get the same thing. So another reaction to make amines is called the Hoffman rearrangement. And this actually starts with an amide. So here we have a primary amide. So there's 1 carbon bonded to the nitrogen, so a primary amide. And now a new piece of nomenclature. The alpha carbon is the carbon next to a carbonyl group. So what happens is, in the Hoffman rearrangement, the nitrogen will actually migrate over to the alpha carbon. So the rearrangement happens because you break this carbonyl alpha carbon bond, and then we end up with a primary amine. And notice that the nitrogen is now bonded to that alpha carbon. So in terms of the mechanism, we need to use bromine as an electrophile and then sodium hydroxide and water as a base. And what we're doing is essentially extruding that carbonyl group. So the reaction proceeds through an intermediate called an isocyanate. So I'll draw that over here. And this has a carbon that is sp hybridized at oxidation state 4. And so that's the isocyanate. And then what the sodium hydroxide, another purpose of it, is to basically excise that group there, which is lost as carbon dioxide. And so when that happens, you free up your primary amine. So this is the isocyanate intermediate. Here's the name of it, the IUPAC name. And as we said, that central carbon is sp hybridized. Again, it has a sigma bond, pi bond. So that makes it sp hybridized, and it's at oxidation state 4. So we count that carbon. We have 1, 2, 3, 4. So oxidation state 4. And essentially what that is telling us is that carbon is really electrophilic. And it wants to react with something, and then what happens in the mechanism, it's ultimately cleaved off. Another type of rearrangement that's used is called the courteous rearrangement. And so this starts from an acyl azide. So we know that's an azide. And then the carbonyl group is sometimes called the acyl group. So we're at oxidation state 3 in the acyl azide. We see that alpha carbon, and what happens is the azide will migrate over under the influence of light and heat, and in the presence of water, we end up with that primary amine. And so what happens is in the Hoffman and Curtius rearrangements is they're both cleaving out or extruding that carbonyl group, which is lost basically as a gas, and you form the nitrogen bond to the alpha carbon. So in these cases, you're ending up with a primary amine. So once we have the amines, what can we do with them? One reaction is called amidation, where we're taking the amine and we're going to form an amide. So the reaction is called acylation, and it will produce the amide. And notice we can only use primary and secondary amines to do this, basically because you need an NH bond that'll essentially be lost under the reaction conditions. So here we have a primary amine called propane 1 amine. We're treating it with an oxidation state 3 functional group called benzoyl chloride, and essentially the primary amine is going to become a secondary amide. And so sometimes this is called lasso chemistry, where we're losing an H into Cl, so that's why we're using base, and we're using a biphasic mixture of dichloromethane and water, where essentially the organic product stays in the dichloromethane and the inorganic stuff goes into the water. So notice the retention of oxidation state 3 in the amide from the reagent that we're starting with. Amides are a special functional group of the carboxylic acid derivatives because they are heavily influenced by resonance. And this is due to the oxygen being more electronegative than nitrogen. So essentially what happens is the lone pair on nitrogen is delocalized onto the oxygen, where now we have nitrogen plus O minus, and then the formation of the more double bond character between the nitrogen and the carbon, and more single bond character between carbon and oxygen. So one thing to recognize in amides is that of the amide functional group NCO, all atoms are sp2 hybridized so that you can delocalize that lone pair up into the oxygen. So again, it needs to be that way because you're forming a pi bond here between the nitrogen and the carbon. A consequence of that is you now have geometrical isomers that can be either E or Z. And for amides, these are oftentimes called rotamers. And so Z means Z is equivalent to cis, And how do we determine that? So if we identify the two atoms of the pi bond highlighted in red, and then we assign priority based on atomic number to each group, and then compare where the priorities lie. So nitrogen has H and C, so C is priority 1, H is priority 2. The carbon has oxygen and carbon. Oxygen's priority 1, carbon's priority 2. The ones lie on the same side, so that's cis or Z. And so the resonance form of an amide can be seen spectroscopically in two ways. So in IR, the carbonyl stretch is typically below 1700. And again, that's because the carbonyl has more single bond character in an amide than any other, say, carboxylic acid or ester or any sort of derivative like that. It's also seen in the proton NMR because of the geometrical isomers. So for example, if you consider that solvent, which is called DMF, dimethylformamide, you would initially look at this and say the methyl groups are one set, the H is another. So you would say there's two hydrogen sets in a ratio of 6:1. However, if we consider a resonance form where now you have that double bond, the methyl groups are actually differentiated in their relationship to that hydrogen. So this relationship would be cis, and then this H to methyl here relationship would be trans. So those methyl groups are actually differentiated, and you see that in the proton NMR where these occur as two different singlets that integrate to 3 rather than one singlet integrating to 6. So due to the significant amide resonance hybrids, there's hindered rotation about that CN bond with a rotational barrier of about 90 kilojoules per mole. And if the thermal energy at room temperature is about 2.5 kilojoules per mole, you can see that that doesn't supply enough energy to overcome that rotational barrier. And so you actually see these two rotamers, the Z and the E, in proton NMR. So again, this is very important. The hindered rotation of amides. If you go on to take biochemistry, we talk about amino acids forming peptides, which form enzymes. That feature of the amide leads to a lot of function that you see in peptides and enzymes. So the amide bond is also called the peptide bond in biochemistry, and it's arguably one of the important bonds in organic chemistry and life because essentially the enzymes carry out reactions in our body, and they're made up of sequences of functional groups with peptide bonds. The other important thing about amides so I'll just say R1, R2, R3, is that they're pretty resistant to hydrolysis. So that means you would form, say, that carboxylate plus the ammonium salt. So amides are resistant to that process, and that's important, again, because we have a lot of stuff in us that's made of amides, and so they need to be stable under physiological conditions so that we can survive. So we saw that acylation of an amide produces an amide. If we use a sulfonyl chloride, we produce a sulfonamide. So a sulfonamide you can think of as sort of like an acid chloride, except now we're using sulfur, which has an expanded octet. The same principles apply. We have an H into Cl. So we generate HCl that's neutralized by the base. And then we're forming this functional group, N bonded to sulfur, which has these bonds to oxygen, so that's called a sulfonamide. And sulfonamides are stable to physiological conditions, acid-base conditions as well. And so let's look at the pKa ranges of these different amine-based NH bonds. So we saw that a regular amine, just an NH bond, is a pretty weak acid with a pKa of 40. If you form an amide, that drops that NH down quite a bit, 15 pK units to 25, so it's more acidic. And now, if you take that carbonyl and you replace it with this sulfur group, you get the sulfonamide. That's 10 pK units, even more acidic. So you can see how going from CH2 to carbonyl to this sulfone group increases the acidity quite a bit. So amides are important for biomolecules. Sulfonamides are used in drugs. So these are called sulfa drugs. And sulfa drugs generally contain a sulfonamide group, so you can see that collection of heteroatoms that's present. And whereas sulfonamides are unlike amides in the sense that they do not have this issue of geometrical isomerism. Again, that's due to the relationship of the nitrogen to the sulfur in periodic table. So if you have CNOF, you can see all of those are in period 2, silicon, phosphorus, sulfur, chlorine. The sulfur is now in period 3, and so that difference in the van der Waals radii really prevents isomerism through resonance. So some examples of sulfa drugs. You have an antibiotic here, sulfamethoxazole, glimepiride. This is anti-diabetes. And so you can see the sulfonamide, and it's also part of this other functional group called a urea. Sulfasalazine is an anti-inflammatory. There's the sulfonamide there. So it's a pretty common functional group in drugs based on its properties. Another reaction of amines is called the Hofmann elimination. And so alcohols in the hydroxyl group, the hydroxyl group is a bad leaving group, so OH minus. The amino group, NH2 minus, is also a bad leaving group. But we can transform it into a good leaving group using some SN2 chemistry, and then we can do an elimination reaction. So it's a two-step process where we're treating the primary amine with excess methyl iodide. And because that amine has a lone pair and 2 hydrogens, what essentially happens is we get 3 methyl groups. And now the amine is an ammonium salt. And so that nitrogen is now a better leaving group. So we can treat with a base, silver oxide. And that's going to deprotonate one of the alpha CH bonds. And so the way this happens is, here's our carbon of interest. We have 2 alpha carbons. One has 3 hydrogens, the other has 2. The alpha carbon with the most hydrogens is the one that undergoes the reaction. So the base will abstract that hydrogen. We do an elimination, so E2 as we learned in organic 1, to end up with the alkene. And so we can see that of the 2 sp2 hybridized carbons, there's 1, so this is a mono-substituted alkene, the least substituted alkene. So what about this reaction here, a slight variant? We have a primary amine. When we treat with methyl iodide, the intermediate we form is now the ammonium salt. So we're looking at all of the alpha carbons. So here we have 1, 2, 3 alpha carbons. The one with the most hydrogens is going to be this methyl group. So that's where the elimination will take place. And so the double bond has to start at carbon 3, go to that methyl group, and we would get D as the correct response. So A is the intermediate. B and C happen from elimination of the other alpha carbons. But again, what's guiding us is the alpha carbon with the most hydrogens is where the elimination takes place. And another reaction of amines is called the Cope N-oxide elimination. So N means nitrogen. Oxide means we're putting a sigma bond to that nitrogen, to oxygen. So because the nitrogen lone pair is nucleophilic, it can be oxidized with a reagent we've seen called MCPBA, which is a peroxide. Or we can use hydrogen peroxide, in which now the amine lone pair will attack one of those oxygens. We form this N-oxide. So notice the charges, N is plus, O is minus. And what that's going to do is an elimination now of a beta hydrogen. So here's our alpha carbon. We have 2 beta carbons, each bearing hydrogen. And so what's going to happen is an abstraction, an elimination, and then the loss of that nitrogen group. So how many total beta hydrogens does the N-oxide contain? There's 3 here. We'll call that beta prime because it's different. That's 2, so we have 3 plus 2. We have 5 total beta hydrogens. So the question says if the syn elimination occurs from carbon 1, 1, 2, 3, 4, 5. So from carbon 1, the beta hydrogen, what is the name of the product? So the way this happens is the oxygen will abstract that hydrogen. We do an elimination, and then we break that CN bond. So we have a 5-carbon chain with a double bond at position 1, so this is 1-pentene. So this question is asking which hydrogen must be abstracted if we want to form trans 2-pentene. So there's pentene. We put the double bond at position 2 to 3. There's the trans isomer. And so if we draw in carbons 1, 2, 3, 4, and 5. This was a beta carbon. Carbon 3 was also beta. So we need to eliminate a hydrogen from carbon 3, and now we need to pick out which one. And the way to do that is essentially we're choosing between this one and that one, is to draw a Newman projection where we need the chain to basically be in a zigzag conformation. So the first thing I'll do is a bond rotation where I'm putting the methyl group at carbon 1 in the plane. And so that's going to make this nitrogen come out. And so we have to then look at H, and we see that the front hydrogen here is on the same face of that N oxide. So when this nitrogen oxygen bond is on the same face as that hydrogen, the elimination will happen to give you the trans or E geometry. So this has been a screencast on the reactions of amines that are important in terms of introducing nitrogen into the molecule, forming amides, the resonance structures of amides and how they're differentiated using IR and NMR, as well as forming sulfonamides, and then a couple different rearrangement reactions to form alkenes.